All right. In classic UAA fashion, we'll start a few minutes late as the stragglers come in. Especially thanks to everybody for being here after the semester's over and on a nice sunny day where it doesn't feel like we really should be in school, especially after yesterday. So thank you very much, everybody, for coming to Roxanne Beltran's master's thesis defense. And we have people here from the UAA community. We also have Roxanne's parents have come in from California, and her fiance Patrick from California, and her best friend Beth from California as well, I'm assuming. Up here we have my grad student Amy, who's currently in Svalbard, but can't participate. Is going to participate this way. And usually, you know, thesis defenses are a great time in the lab for all the grad students to get together and have a party afterwards and whatnot. But as you can tell, Amy's in Svalbard, so it's kind of hard for her to participate actively right now. One of my other grad students, a couple other grad students in the lab. So before I start off with Roxanne's thesis defense intro, I want to do since she's leading the way for the rest of my grad students this year. We've got Roxanne's defense today. On Friday, another one of my grad students, Pearson, will be defending.
Get with the program.
I presented a modified file one.
Hey, Dan! Put your room on mute.
Yeah.
I think they can hear us, by the way.
That would be Roxanne's reading group from California, which is participating also remotely. So my other grad students who are finishing behind Roxanne, since she's starting off this semester, is Linnea will be up from Juneau on Friday to defend her PhD thesis. And then a month from that, Michelle Shiro will also be defending her PhD thesis here. Michelle this week is not in Svalbard or California. She's in Saskatoon learning how to do ultrasounds by sticking things in weird places of animals. So yeah, her thesis defense will be interesting as well. But to give you a little bit of intro to Roxanne and her thesis project, Roxanne's a California transplant like many of us here. I didn't meet her when I was a postdoc in Santa Cruz, but she was an undergrad student in the same lab that I did my postdoc in. So there's her with her banana slug. And she came to my attention because another one of the grad students I was working with said that she had this rock star undergrad who was doing amazing things studying seal whiskers. And I must say that Roxanne does adore seal whiskers. And she has since published 2 papers on seal whiskers from her undergrad thesis, plus another paper, all as first author from undergrad work, which should tell you something that Roxanne is pretty much of a rock star that she was advertised to be. The other thing that might clue you in on that fact is that we are now 18 months after she arrived in my lab, and she is defending her master's thesis. I have been chair of the UAA grad committee for more years than I want to think about, and this is the fastest that any student in our program has ever finished their graduate degree, so that is definitely to be congratulated. Roxanne is also hugely well-traveled while doing this amazingly speedy amount of work. And actually, it's more than 100,000 air miles because I forgot to return her back to UAA every time after I did this math. She's made 3 trips with us to the Antarctic to do the research she's presenting today. She's also worked as a field assistant on the Pribilof Islands with one of her other committee members, Ward Tasta. And she's helped out on field work in California and kept that going while she was here, and also visiting fiance and friends and family. She's taken a programming class that was offered for graduate students in Germany to learn some of the programming methods that she's going to talk about today. And she's given a variety of different oral presentations at meetings in California, Alaska, and New Zealand, and won awards for some of those oral presentations. She's also been a really good ambassador for science. One of the things that Roxanne and my other grad student, Amy Kirkham, have gotten up and running while we've been working on this thesis, on this research project, is we've been going out to the school districts in Anchorage and working with other people, a collaborator in Tennessee, to deliver information about science, about our project, all sorts of different aspects to the Anchorage school kids, and there were more than 1,500 students reached last fall with this program, and it's continuing now. And we have Patches, the lab up in the seal, which students get to put little patches on, and also evidently makes a really great pillow if you're really late. Roxanne is nothing if not enthusiastic. She's been fun. It was really fun to have in the lab, in the field, on the ice, working in Antarctic, C-130 flying to the Antarctic. Anybody who can look that enthusiastic while on a plane for 8 or 10 or 12 or 14 hours is really quite impressive. And she's even had a great time out on the Pribilofs and done really good work out on the Pribilofs where it's cold and snowy and foggy and whatnot. And she does things like this, which scare the living out of me. Not something I want to do. And the other thing I want to point out is Roxanne has great expressions. And whether that's, what she looks like when she's having fun in the field or what she says, it's always fun to interact with her. And everybody in the lab's had a lot of fun having her there, whether it's stinky or not. And she might not always be the largest member of her field team, but certainly the SEALs do pay attention to her, and she pays attention to the SEALs, and she's got what I like to call great field hands. She works really well in the field with a lot of different people, a lot of different critters, a lot of different skills and things like that. And she also has a love for Oreos. We got stuck overnight in a field hut, and I have never seen anybody put so many innards of Oreos together into individual Oreos. I think she ate all the Oreos in a day. And she likes them whether she can eat them or whether she can sleep on them. So as we get to a thesis defense, a lot of grad students are wondering, well, what am I going to do next? It's kind of a time for transition, and sometimes it can be a little scary. Roxanne is, in fitting with how she's been as a grad student, continues to take on the world. She has successfully awarded a National Science Foundation Graduate Research Fellowship. So she will start in the fall as a PhD student at School of Fisheries and Ocean Sciences to build on the work that she's going to be presenting to you today. So she already has the next couple of years of her life planned, and if I know anything about Roxanne, that will be the 3-year PhD, kind of the fastest PhD program on record. So with that, I'll let you let Roxanne start to tell you about what she's been doing, and let her get going on her thesis presentation.
Thank you so much, Jen, and thank you all for being here today. I'm very excited to talk to you about the work that I've been doing over the past year and a half or so, building a model to predict impacts of environmental change on woodall seals. Woodall seals are the most southern living free-ranging mammal. They can live up to about 80 degrees south, and in Antarctica where they live, it's a very extreme and seasonally changing environment, and so they have a lot of adaptations that allow them to both survive and thrive in this extreme environment. For instance, they have very thick blubber layers and very high percent fat content within that blubber. And they have a capital breeding strategy, which means that they can energetically finance lactation via energy stores that they've accumulated throughout the entire year. Now, at the beginning of the Weddell seal calendar year, which you can see here on the left, starting in January, is the annual molt. And that occurs for about 2 to 3 months during the warmest period of the year. During this time, they're hauling out and they're making their skin very warm to promote hair regrowth. Just following the molt is the very cold winter period where these animals are foraging for a very large proportion of time in order to both regain the condition that they've lost during the previous molting period, but also to gain condition in anticipation for the upcoming lactation period, which happens starting in about mid-October, just after birth, and happens for about 42 to 45 days, during which the moms can lose up to about 40% of their body mass. These activity patterns that I'm talking about are very evident when you plot activity as a function of time. So I'll walk you through this graph. What you're seeing here is each box is color-coded by the proportion of time each animal spent hauled out, where the warmer colors are a larger proportion of time hauled out, and the cooler colors are a smaller proportion of time hauled out. On the y-axis, each row is an individual seal, and each column is a week of the year, beginning in January on the left and going through December on the right. So what you'll immediately notice is that there are 2 groups of animals here. This bottom group of animals were seals that were instrumented with time depth recorders, which collect depth data every 6 seconds or so and can be used to make inferences about activity patterns. And these animals were instrumented as part of Dan Costa and Jen Burns' NSF-funded project that was on overwinter woodall seal diet behavior. They were instrumented just following the molt, so in that February period, and then the instruments were recovered at the very beginning of lactation here in October. The second group of animals that's on the top of the slide is the animals that were instrumented over the summer period. So these animals were given tags during this time of the year at the very end of lactation, and then those tags stayed on the animals through the end of the year and into the beginning of the next year, and were recovered either at the beginning, middle, or end of that molting period. So what you'll immediately notice is that during the winter period, again, those bottom seals, these animals are spending a lot less time hauled out, as evidenced by the cooler colors, because they're foraging a lot, like I said, to try to replenish those lipid stores. And then during the summer period, they're hauled out for pretty extensive periods of time during both the lactation and the molting period. Now, the reason for these seasonal changes in both body composition and in activity budgets are largely due to the seasonal sea ice extent in the Antarctic. From the ice minimum that you can see here in about February to the ice maximum in September, the Antarctic continent can almost double in size. And so these animals have, like I said before, a whole suite of adaptations that allow them to sort of buffer against times where they might not be able to forage as much. They also have really well-developed teeth and really flexible jaws that allow them to maintain breathing holes in the ice throughout the entire year, despite the very low temperatures. But in addition to these baseline seasonal ice changes, researchers have noticed a reduction in ice across the Antarctic region. What you're going to see in this animation is colors that are turning more red, or areas where the ice is disappearing most quickly. And so you'll notice that that's in the west part of Antarctica, so here on the West Antarctic ice sheet and the Western Antarctic Peninsula up here. The seals that we deployed instruments on that I showed you data from earlier are in this region right here, just around McMurdo Station in the Ross Sea. And you can see that this has been a pretty stable place across time. The ice hasn't changed too much. And so these animals serve as a really good baseline indicator of normal wood-elf behaviors and body mass condition changes over time. This reduction in ice can have implications for these top predators, both through indirect and direct mechanisms. As far as direct mechanisms, predators are allowed into the area if there's less ice that maybe weren't let into the area before, which of course can have implications on their vital rates. And it also can increase the distance between their foraging places and their haul-out places. And so they're forced to work extra hard, both in order to accumulate the energy, the subcutaneous lipid stores, and to survive through certain times of the year. Also, indirectly, this reduction in sea ice can alter the typical primary productivity regimes in the region, and so can lead to decreased foraging efficiency and less mass gain for these animals. In addition to threats from reduced sea ice, we also see threats from an exploratory fishery that has been established in the Ross Sea. So again, this is Antarctica. We're looking at this area with the blue star, so sort of this chunk of the pie right here. This fishery is primarily for Antarctic toothfish, or Disosticus mawsoni, which is about 40 times larger and about 5 to 10 times more energy dense than most of the other fish species that these animals can have as prey, and so could provide an important energetic source for wood-elf seals. This graph on the right is both the catch limit in blue and the reported catch as a function of time, beginning in 1997 on the left here, when the fishery began, and going through 2013, when this report was created. And you can see that both the catch and the catch limit have increased across time and have sort of stabilized around 3,500 metric tons. But there are talks about increasing the potential catch limit and therefore the actual catch in this area. And because of that, CAMLAR, who manages the fishery, which is the Convention for the Conservation of the Antarctic Marine Living Resources, has modeled these fish's biomass across time. Beginning again at the beginning of the fishery, the biomass of these toothfish was about 70,000 metric tons. By 2013, when this report was created, represented by this vertical line, the biomass of these fish had dropped to about 75% of original levels, and the predictions are that the biomass will decrease to about 25 to 50% of the original biomass by the year 2050. So many papers have recently posited that these toothfish could be really important components of the wood-elf seal diet, and have even attributed some decreasing body condition, decreasing body mass, or the disappearance of some smaller populations to the expansion of this Ross Sea toothfish fishery. So it's important to understand the implications of both fisheries and changing ice extent on these top predators. One way to do that is to conceptualize the links between these. This top conceptual model was adopted by PCAT, which is the Population Consequences of Acoustic Disturbance, and I'll sort of walk you through it. On the left here, we see this direct perturbation, such as a sound source, and then eventually that leads to a population effect. But we need to understand the sort of temporal sequential mechanisms that occur within that in order to go from a perturbation to a population effect. So they've posited that the sound creates a behavior change, which you can see here, such as diving deeper to avoid the sound or going farther to avoid the sound. And this behavior change can then have implications on life functions. So if the animals are doing something different behaviorally in order to avoid the sound, they could not be doing something else, such as breeding or nurturing their pup or feeding. And this, of course, could have implications on vital rates, which then have population effects. In indirect perturbations, such as climate change or sea ice reductions, we often see that the life functions and behavior changes happen in the opposite order. So I've taken these two terms here and I've flipped them in this bottom section. So something like climate change can immediately cause a change in life function. For instance, if the animals are feeding and their feeding is not as efficient, they could be required to change their behaviors in order to sort of gain back the mass that they lost from that decreased foraging efficiency. And that behavior change then could have implications for vital rates, which could eventually lead to a population effect. So once we start to understand the links that happen between these things to go from a perturbation to a population effect, we're able to then manage those sources, both direct and indirect, of potential changes in vital rates. Many of the mechanisms that link these two things together are energy-based. So this conceptual model was put together by Costa in 2012, and it shows how energy flows into and out of an individual mammal. So you can see prey goes into the system on the left here, and then some of the energy is lost to both fecal and urinary energy as well as heat output. And then what's left is metabolized and synthesized and is allocated to these different requirement categories, such as growth, reproduction, and repair. And then, of course, the output, in addition to adult survival, is the production of the young, which gives you those vital rates that you can then compare across these different categories. Many people have attempted to model that energy budget or the energy flow either through individuals or through populations. And so that started with the EcoPath or EcoSim models. This particular one was by Palomino in 1984. And it shows how energy runs through a system. This is sort of just a figure on the left to demonstrate what this type of model looks like. So you can see this energy here that's being created at the very bottom trophic level and is going up through the trophic levels. Of course, the trophic levels are linear. There's no uncertainty or seasonality incorporated here. And so there are a lot of limitations to the inferences that you can make from this. Some of the more recent energetic models, like that created by Winship in 2002 for stellar sea lions in Alaska, have considered multiple age classes, have incorporated seasonality and uncertainty, which has been great and has allowed for food requirements for populations to be calculated where they really weren't understood before. However, there are often a lot of assumptions that make it difficult to extrapolate this model to different systems. For example, if the cost of molt or cost of thermoregulation are not included, then we can't use this model to test hypotheses about how things like changing temperatures could impact vital rates. In a more recent paper, Sean Noren in 2012 made an energy model for Pacific walruses, sort of took the model from Winship and did a couple other things with it. She considered reproductive status and simulated climate change scenarios to ask the question of how climate change scenarios might impact reproduction, and also went ahead and included the cost of molt. Unfortunately, because in this model the activity budget for these animals was fixed at a given proportion during certain parts of the year, the animals in the model simulations were not allowed to behave plastically. They weren't allowed to change their behaviors in order to sort of adapt to the conditions that they were in. That same year, Testa came out with this model for mammal-eating killer whales that allowed the animals to adapt their behavior. So based on a decision-based activity matrix, the animals were allowed to interact with both each other and with their environment in order to make the most optimal decision for those animals. And he even took it one step further and expanded this via population dynamics to sort of predict how the population would do under certain scenarios. Unfortunately, because killer whales are not as well studied as something like a fosid seal, a lot of the parameters were not available in the literature, and so either assumptions or extrapolations had to be used, which he notes in the paper can also lead to some limitations. Most recently, Kuroda et al. In 2014 created Again, an agent-based model, similar to the tested paper that used a decision-based activity matrix that allowed the animals to sort of change their behaviors. And it was also programmed in R and made freely available to people so that other researchers can sort of adapt this model and use it for other purposes. Unfortunately, this model did not account for life history events such as lactation and, of course, the molt that happens in pinnipeds. And so there were, again, limitations with this model. So I've introduced you to the reasons why it's important to represent these links mathematically, and I've shown you the limitations that exist in the current literature. What I wanted to do for my master's thesis was to create a dynamic agent-based model using R, freely available to people, that would explicitly link physiological processes and behaviors with both energy consequences as well as population-level consequences like vital rates. I sought to fill as many of the gaps in the literature that I could by doing things like incorporating the cost of molt reproduction and thermoregulation, including empirical sea surface temperature and air temperature data, incorporating uncertainty into every time step in order to sort of buffer against inaccurate parameter estimates or come up with a range of output values. I allowed my animals to behave in a way that they could choose based on certain limitations, and so they could change their behavior based on extrinsic conditions. I allowed them to have a bit of fluctuations in the timing of their life history events. And fortunately, because Weddell seals have been so well studied across time, I was able to limit the number of approximated or extrapolated parameters and was able to fortunately find most of the parameters I needed from the literature. So after I describe to you model development, I will walk you through how I validated the model to have high confidence that this model was accurately representing the system. And then I will run you through a sensitivity analysis and a perturbation analysis to show you that, first of all, we can start to understand the sensitivity of output parameters to changes in input parameters, but also that we can start to make inferences about how changes in input parameters could relate to what's actually happening in the real world. Following that in the discussion, I will tie it back together and show you how I've used this model to essentially tie both direct and indirect perturbations to population effects in Weddell seals. And these will be at the bottom of the slide so you can keep along. Great, so I'm going to jump right into the conceptual model here. My model ran for a total of 365 days in the life of the seal in 15-minute time increments. So in total, there were about 35,000 time steps per simulation. This conceptual model represents one time step. So starting on the left is the beginning of the time step. For each of the animals, the reproduction, maintenance, and molt requirements are first calculated, and then the animal evaluates both its energy stores and its current life history event constraints in order to choose an optimal activity. After the animal chooses that optimal activity, it balances the energy after calculating the activity and thermoregulatory requirements, and then either deposits that extra energy as subcutaneous lipid stores or will catabolize tissues in order to fill those requirements. Following that, a daily mass and body composition change is calculated, and then those become the starting parameters for the next time step, and that runs through about 35,000 times per individual. To give you an idea of the individual life history parameters that were incorporated into this model, I've sort of briefly outlined them. For the individual animal, I used a straight length value as well as a girth value in order to have a physical model for thermoregulation. I also incorporated a blubber depth value, again, for that thermoregulatory model. To represent the year in the life of the seal in an appropriate way, I needed to constrain the molt and lactation timing using both a start time and then the duration of that life history event. So it would happen at an appropriate time and for an appropriate length. In order to do that, I used empirical data that was given to myself and Jen by Bob Garrett. And these are essentially pupping dates for Weddell seals across different years. This is just a density histogram of them, where the 2010 pupping dates are in green and the 2014 pupping dates are in blue. And you can see that they align really well across the years, where the peak is about 301 days after the beginning of the year, or about the middle of October. Because those are so similar across years, I lumped them together and then just used the average and standard deviation from that pupping date in order to assign my stochastic simulated seals with a pupping date. I did the same thing for the molt start date with data that Jen and I had collected in the Antarctic. We essentially denoted molt progression in Weddell seals, and I took the animals that we knew had just started the molt and I plotted those in a density histogram. You can see that it peaks around about 34 days after the beginning of the year, which is about the beginning of February. And again, use that mean and standard deviation as well as the normal distribution to then assign a molt start date for these animals. Now, to represent lactation, in Waddell seals, I told you a little bit before, you can see this is a very young pup, and the mom is still pretty fat. And then about 30 to 40 days later, this is the pup, and the mom shrinks down quite a bit. They can lose, like I said, up to about 40% of their body mass. So to represent this in the model, I had the pup as sort of a separate entity and the mom as a separate entity. Based on the energy density of milk and the biomass of milk that the mom was producing every minute or second, the mom would produce that milk, and then the pup was able to take that milk and deposit it as fat. So I was able to track both pup mass and mom mass as well as condition. For gestation, I used a fetal growth curve produced by Young et al. In 2005 and plotted fetus mass as a function of time, where you can see on the y-axis is its fetus mass. This is the entire simulation. So the gestation period starts about here, and then the body mass increases of the fetus until parturition, and then of course that's in a separate category. In addition to fetus mass, I took the energy density of the fetus, which is based on the proportion of the fetus that is comprised of lipid, which is plotted here as a function of time from the beginning of gestation to the end of gestation, and combine those two things in order to estimate the cost of producing or maintaining that fetus throughout the entire gestation period at every time step. That combined meant that the cost of gestation, which is plotted on this right plot here as a function of time, was highest at about the beginning and middle of the third trimester, which makes intuitive sense. For the thermoregulation model, briefly, I wrote a custom code in R that holds empirical weather data from a couple sources on the internet. The first was the NOAA Optimum Interpolated Sea Surface Temperature, which is weekly means, and then I also pulled air temperature, cloud cover, relative humidity, and wind speed from the National Center for Atmospheric Research in 6-hour means. And so those can be pulled from any date and time in any geographic location. This is what you get when you put in the coordinates for McMurdo Station, where we study the seals. This is air temperature on the left y-axis as a function of time from January to December. So you can see what I'm talking about. When the animals are molting during this time, it's the warmest part of the year, so that's why they're molting then. And then, of course, the air temperature gets very cold during the winter period. On the right y-axis is water temperature, so you can see a similar pattern there, where the temperature of the water is coldest during the middle of the winter. So those empirical temperature and wind data go into this thermoregulatory model, which assumes that the animal has, an insulating blubber layer and then a core that's producing that heat. I assume that heat is lost when an animal is water through convection, and when the animal is in air, it's lost either through convection from the upper surface or conduction from the lower surface. This requires knowing a couple things about the animal, including its surface area, which is calculated from mass, and also the temperature of its skin. This is a little bit debated in the literature, what exactly the temperature of the skin is in different environments. So I simply used this regression that was published by Mellish et al. Up here, which is skin temperature as a function of air temperature. So given the air temperature that the empirical data were showing, I could assign a skin temperature for that animal for that given time step. So the result of that, you see on the right, I took out the numbers so you just focus on the patterns. On the x and y axes are skin temperature and air temperature respectively, where you see that the warmer air temperatures equate to warmer skin temperatures, which are in this close quarter here. And then, of course, back here are the colder air temperatures, which means colder skin temperatures. And then, of course, the cost of thermoregulation is on the z-axis here. So you can see that the cost of thermoregulation is highest when air temperature is the coldest, which makes intuitive sense for these animals. For the molt, I calculated surface area again, and then calculated the cost of producing the new fur coat. I did this by including the length and density of the fur along with the energy density of that total fur mat, and the deposition efficiency for protein, which I used as sort of an approximation for the efficiency of producing hair. And I also constrained the timing of molt a bit by incorporating the time activity budgets from the free-ranging animals that I showed you before. Because not much is known about how molting progresses in these seals, how fast it goes, how many days hauled out it takes them to molt, I used the percent time on average that the free-ranging animals had spent hauled out during the molt, and then took that as sort of the rate that an animal needed to be hauled out for in order to complete the molt in the given time period. Because wood elk seals are relatively inactive on land, I did not incorporate a cost of activity on land, but in water I incorporated the cost of swimming, assuming that an animal, like this representation of one, moving through the water column incurs some cost because of drag and needs to have a propulsive force that will propel it through the water at a given speed. And so that's how the cost of swimming is calculated. Now, all told, that was about 36 functions, which are listed here, as well as about 88 parameters, just value parameters. And those were combined with about 1,200 lines of R code. So it was a little bit complicated, but hopefully I've outlined it pretty simply. The activity selection model was one of the most complex parts of the model, so I'm going to try to explain this very slowly and clearly. There were 4 potential activities that the simulated animals could choose at every single time step. The first one was that they could choose to molt, meaning that they would haul out, make their skin nice and warm, so that the skin temperature was constrained when they were molting at 17 degrees Celsius, which we know is the minimum skin temperature required to regrow fur successfully. They could choose to nurse their pup, so of course during the lactation period they would do this on and off, and those energy requirements would be the cost of lactation and just the cost of maintenance. They could choose to forage, which would incur activity costs because the animals are swimming, but also would allow them to obtain prey. And then they could finally choose to haul out, and this would be a very low cost, but they could choose to do that if their body condition was adequate, etc. So for the decision about whether or not the animals wanted to spend a time step molting, I created an expected molt completion regression, which you can see on the top left. This is the expected molt completion from 0% to 100% on the y-axis, and then on the x-axis, this is the date of molt start and the date of molt end. So I assumed that there would be some sort of linear progression from the beginning of end to the molt, where they had not completed the molt at the beginning and had completed the molt at the end. Which means at each time step, I could evaluate the number of time steps they'd spent molting, and therefore the percent of molt they'd completed. And if they fell below this expected progress trajectory, then they would prioritize molting. Whereas if they fell above that trajectory, they would prioritize some other behavior, which is what you're seeing in these checkboxes here. So if molt progress is satisfied, then it might choose one of these other 3 activities, but if the molt progress is not satisfied, then it will prioritize molting. This is the same for the lactation progress, except instead of on the y-axis having 0 to 100%, I have the expected pup mass from the birth mass at the bottom of the y-axis to the weaning mass at the top of the y-axis. And this is as a function of time, again, from the date of parturition, which is the very start of the lactation period, through the date of weaning. And so again, at each time step, I can evaluate whether or not the pup has gained enough mass to be following that expected mass trajectory. And if the animal has fallen behind that, then the mother will prioritize nursing their pup. Hauling out and foraging were a bit more complicated, and I wanted to draw in empirical data so that the animals were doing realistic behavior switches as opposed to changing behavior sporadically every 15-minute time step. For this, I used data that Michelle Shiro and Jen's lab had calculated for wood elk seals over winter from the same seals that I showed you earlier. And this, on the left side, is the average amount of time that animals spent foraging in one given day, which you can see is an average of about 17 hours, plus or minus 3 hours, or equivalent to about 70 time steps for a mean. And then I converted that density histogram into a binomial logistic regression, where the mean amount of time they spent foraging during the day then became this halfway point, where the probability of hauling out, given the amount of time they spent foraging, was 50% if they spent an average amount of time during that day foraging. That way, if they were spending more time than that during the day foraging, then there would be a lower probability, a higher probability of hauling out. Whereas if they hadn't spent very much time foraging throughout a day, the probability of hauling out would be very low. And what this looks like in the model is pictured above, where the probability of hauling out, which is on the y-axis, climbs and then finally reaches a point where when I select a random number between 0 and 1 at that time step, if it falls below the probability of hauling out, then the animal will choose to haul out and will switch its behavior. So what you're seeing here is at the beginning of this time step, at the beginning of the simulation, this particular individual was foraging, and as it foraged across time for about 50 time steps, the probability of hauling out climbed and climbed and climbed until the point where my random number that I drew fell below that probability. And then during this gap here, the animal was hauled out. And then again, the animal began to forage during the second curve, and the probability of hauling out again grew. And so this happens repeatedly throughout the entire simulation. The probability of foraging was similar, where I took empirical data that Michelle had calculated. Animals spend an average of about 6 hours plus or minus 1 hour hauled out, so I can convert that again to the sigmoidal curve, where I calculate the probability of foraging given the amount of time that they've spent hauled out. And for this, I also incorporated body mass, because we know that if body condition is poor, the animals have a very high probability that they'll want to forage, despite the amount of time that they've been hauled out. So I multiplied the the probability of time foraging given the amount of time they've been hauled out by the probability of forage given body condition, where if they're very good body condition, the probability of them foraging is relatively low. So if the animal decided to forage, it was allowed to take in prey, and that was given sort of into the energy budget, and the energy budget was recalculated. A lot of people in these types of models will sort of arbitrarily pick a prey availability, or will sort of tune the model to fit whatever behavior the animals need to be doing. They'll sort of fine-tune the prey availability. And rather than doing that, I decided that I wanted to use empirical data. So I took time depth reporters, again, from these overwinter and oversummer free-ranging animals, who we also happen to have body mass and body condition at both tag deployment and tag recovery. And I was able to essentially calculate the amount of prey that those animals must have taken in order for those changes in body store and body mass to be true. So I'll walk you through that. On the top left, you're seeing a plot of dive depth as a function of time for a subset of about 3 hours, where the sort of brown-colored dots are time spent on the surface, where the depth of the animal is 0. And what you're seeing here is the activity pattern of diving happening. So I was able to take these dive records and pull out the amount of time that each of the animals had spent hauled out versus the amount of time that they'd been foraging, which consisted of either diving or feeding. And I was able to calculate an average amount of time that these animals spent hauled out and foraging for both the oversummer and overwinter period. Now, by combining that with what we knew about their life history events, if they had gone through lactation during the deployment period, what the temperature was like, and what their cost of thermoregulation might be during that period, et cetera, I was able to essentially back calculate the amount of energy that they must have expended during that deployment period. And that, combined with the deployment length and the body mass and body condition changes we knew happened, I was able to essentially calculate the amount of prey that they must have consumed in kilograms per second for those mass change values to be true. So this gave me this gave me a value to input into my model, where my simulated seals, for each second that they spend foraging, they get approximately this amount of prey. Now, once they take in that prey, of course, it goes through a couple inefficiency processes, like I've described before, where some energy is lost to feces, urine, and to the heat increment of feeding. And so, for example, if 6 kilograms of prey are taken in, with all the inefficiencies, that amounts to about 3 kilograms of prey. So again, these values are all pulled from mean and standard deviations, and so this changes at every time step. So once the prey energy that's taken in is calculated, and once all those energy requirements are calculated, the excess energy is then calculated, and it can either be positive or negative, where if they have excess energy, they're depositing that as subcutaneous lipid stores, and if it's negative energy, then they have to essentially catabolize their tissues in order to produce enough energy to fulfill those requirements. Now, at each time step, I mentioned this a little bit before, I incorporated uncertainty using Monte Carlo simulations. So most of the parameters that I was able to find in the literature had a given distribution. They were either normal or uniformly distributed. And I had either a mean and standard deviation or a minimum and maximum for those parameters. So for parameters that were assigned once, like the birth mass of the pup that was just decided at the time of parturition, I was able to pull one stochastic value at the very beginning of the model. The way that was done was taking that distribution mean and standard deviation, which you can see here. I pulled 10,000 values of that specified distribution and then randomly shuffled them and selected one so that each run of the model would be different. Therefore, there would be stochasticity between the different individuals that were simulated. For other parameters that were assigned at each time step, like the prey availability and the energy density of the diet, I did the same thing, but I did it at every single time step so that every single time step of the model stochastically incorporated that distribution of parameter inputs. So this is what you find when you put all that stuff together. On the y-axis, you see body mass of the simulated animals. This is just a subset of 10 animals. And on the x-axis, you see time steps, or the time of the model, where the 0 time step on the left, again, corresponds with January. And on the right here at 35,000 time steps corresponds with the end of the year in December. So the mass change patterns that you're seeing here are what we would expect. You can see that at the very beginning of the year, the animals are foraging a bit to sort of regain that condition, and then they begin to molt, and during that molt period, they're losing a little bit of mass. Following that is the winter period, where I told you they gain quite a bit of weight, and then that weight gain starts to sort of tail off once gestational costs become relatively high during the third trimester. And then this is when parturition happens, and during the lactation period, they're dropping, like I said, up to about 40% of their body mass. And then at the very end of the year, they're foraging a little bit to increase their body mass again. And what this looks like in terms of box plots, if you bin all of those 10 animals together, it's the same sort of trajectory. It just looks a little bit cleaner, where again, they're losing a little bit of mass during the molt and a lot of mass during lactation. So the reason for those mass loss changes can be easily looked at with this type of model using R. The left plot that you're seeing is the energy expenditure as a function of time in weekly bins, where you can see this drop in energy expenditures during the molt because they're not very active during this time, so they don't have a lot of swimming costs associated with this time. And then, of course, the lactation period over here, you see that the energy requirements are really high. Now, if you look at the prey consumption, which is this plot on the right, plotted as a function of time again, during the molt, because they're not very active and they're not foraging, they don't take in very much prey. And it's the same with the lactation period. You see this huge drop in the amount of prey that they're taking in. So because of the high energy expenditure and low body consumption, that's where the changes in mass come from. One of the great things about this model is the output parameters are sort of spit out into a table that you can use to calculate the average and standard deviation for each of the animals and for a large number of output parameters. And so you can begin to sort of compare these output parameters across different individuals or different simulations. There's a lot of different things you can do with these output tables. So once the model is created, like I said before, I wanted to make sure that it accurately represented the system. So I showed you this activity plot before, where again, this is the overwinter seals, this is the oversummer seals, and they're color-coded, where the warmer colors are a larger proportion of time spent hauled out, and the cooler colors are a smaller proportion of time spent hauled out. And this is the simulated seals. So you'll immediately notice that the blues and yellows during the overwinter period, more or less, maybe with a little bit of uncertainty incorporated, line up relatively well with the free-ranging seals. You can see the lactation period here, where the animals are hauled out between 80 and 100% of the time. And of course, like I said before, in the empirical seals here, lactation is not represented in any of these boxes because the winter seals the tags were recovered at the very beginning of lactation, and the summer seals were deployed at the very end of lactation. Now the molt period, which you can see here, is a time of largely inactivity for the simulated seals. But if you look at the empirical data, you don't necessarily see those lining up very well. And the reason for that is that in Waddell seals, we're finding with Jen Burns' current NSF project, there is a very particular link in timing between the molt and the reproductive periods, where if animals do not reproduce in a given year, they molt a lot earlier than the seals that did reproduce in a given year. Because these winter seals were instrumented with tags that required gluing the tags onto the animal's head, these were all glued onto animals that had already molted in the January-February period. So they were all skip breeders. They did not reproduce that given year. But these animals that I'm putting into my model are all reproductive seals. And so that molt timing is offset, which is why you don't see that behavior in the simulated seals match up with the behavior in the free-ranging seals. In order to validate the model in a different way, we can also plot things like pup body mass as a function of time. This plot on the left was published in Hill's Thesis in 1987, and you can see from my model that pup body mass as a function of time lines up relatively well with the published values. We can also create tables of model results, which here are in red, and compare those to published values to see how well they align. And after looking through all of those, most of them aligned relatively well. I also ran a sensitivity analysis.
You take a question?
Sure, can I do that?
Okay. Can you go, I'm just getting a little lost. Can you go back to the slides with color on them?
Yes.
So the body mass prediction and the time hauled out prediction, none of these changes in those values are tied to any date in your model or any elapsed time?
They're sequential in time. Is that what you're asking?
Yeah, no, well, no. I mean, it seems like you've got a bunch of, depending on where the seals start out, the initial conditions, you run your model, which is just based on these metabolic costs and their choices, but you see these dramatic changes in their behavior and in their body mass also.
Yeah.
None of those changes are tied in your model to any particular elapsed time or anything.
Oh, I see what you're
Is
asking.
it all just based on the behavior of the...
Yeah, it's all based on their selected behavior. And the selected behaviors, of course, are based on their life history constraints. So the reason that you see such a big behavior change during the molt is because of that molt completion trajectory that I showed you. So if the animals are falling behind that, they're prioritizing molting during that time. And so if they fall behind, then they haul out a lot more. So that's where those big behavior changes come in.
Oh, that's really great.
Yeah.
So, but, and then one more question. It seems like they could start out from a number of initial conditions. What were all the different values that you plug in to make a seal?
That's a great question, yeah. So I ran through a lot of the input parameters, things like starting body mass at the beginning of the year, which we pulled from Jen Burns' current project. We took, the condition at the beginning of the year. We randomly assigned them an activity at that first time step. A lot of the parameters were based on those requirement categories that I explained earlier. Yeah.
I totally lost that part. Then.
Yeah, that's okay. That's okay. I know it's a lot.
Okay.
Thank you guys for bearing with me. Are there any other questions? Okay. Following the validation, I ran a sensitivity analysis in order to see how sensitive the output parameters were to changes in the input parameters. So what you see here is different output variables that we can measure, like the adult mass at the end of the simulation, the adult percent fat at the end of the simulation, and on this other side of the table is the potential input parameters. So energy density of diet was one, prey availability was one, and the efficiency of digestion was one. And for a sensitivity analysis, you essentially change one of the input values by 5%, and then you measure the change in output values. And that gives you an idea of the influence that those input parameters have on the output parameters. So I organized these for easy reading, where the output variables, so these ones here, that are most sensitive are on the left side, and the input parameters that are most sensitive are on the bottom. So if we just take one output variable, like adult mass, you can see that it was, because these are relative values, so the larger ones mean that there's a higher sensitivity. The input parameter with the highest sensitivity for adult mass as the output parameter was efficiency. So digestive efficiency is both a really important parameter and or it's not very well understood in these animals. We see the same thing looking at percent fat, where efficiency had the highest relative influence on the output. And same with foraging, as well as adult survival and lean mass. So from this type of analysis, we can begin to understand which parameters need to be more well studied. In this case, digestive and urinary efficiencies, which have relatively big uncertainty surrounding those parameters, need to be more well studied. In order to demonstrate that this can be used to evaluate potential consequences of perturbations, I ran one example simulation to show you where I decreased the prey abundance by 10% and then with all the same input parameters and looked at what the animals did differently during that simulation. So this is the body mass box plot that I already showed you, where body mass is plotted as a function of time in weekly bins. And what I'm going to show you is the body mass during the perturbation simulation, so how that changes if the animals throughout the entire simulation are not given as much prey per given time foraging. So this is the baseline plot, and you'll see now the perturbation plot. So you can see, same axes, that the mass is decreased throughout the entire year, and the uncertainty is also a lot larger because certain seals are not able to sort of adapt or change their behaviors as well as other individuals. So again, I'll show you, this is the baseline plot, and then you can see the perturbation plot here. So there's a pretty big change there that's relatively noticeable just from the naked eye. If you also look at the same activity plot I showed you before, these are the empirical animals, these are my baseline animals, and then I'll overlay the perturbation scenario here. So what you can immediately notice is that this overwinter period is a bit more blue than yellow, which means that the animals are actually hauled out less and foraging more, which again makes intuitive sense based on the prey availability. You'll also notice that this animal here actually aborted her pup or abandoned her pup, as it may be, at the very beginning of lactation, because she was in such poor body condition that she ended up prioritizing her survival over the pups, which you can see she essentially foraged quite a bit during lactation as compared to the seals that had successfully reproduced. And we can view these differences between the perturbation simulations and baseline simulations as box plots. So on the left box plot here, you see body mass at the end of the simulation as a function of the simulation. So perturbation end masses were a little bit lower than the body masses during the baseline. And you'll notice there's a lot more of spread in the data, where the data spread here is about twice as much as the data spread in the baseline scenario. You also see if you plot percent time hauled out as a function of simulation, that the animals spent less time hauled out during the perturbation scenario than they did the baseline scenario. So again, this can be used to test specific hypotheses about how things like percent time hauled out and body mass could change as a function of extrinsic conditions. So to tie everything up, I hope that I've demonstrated to you today that I was able to successfully create an energetics model that essentially provided these links listed here in red, the links between things like climate events and commercial fisheries to population dynamic in a and seal species. I was able to incorporate uncertainty and consider many costs that had been largely ignored in previous models, including costs of thermoregulation, reproduction, and molt. And I used empirical behavior and mass change data to back calculate empirical prey values instead of fine-tuning the model based on what my animals were doing. With the sensitivity analysis, I was able to highlight parameters that are not well understood, and that should be focuses of potential captive studies that could measure things like fecal and urinary digestive inefficiency, or as the case may be, the exact threshold of body condition or body mass that might lead to reproductive failure in these animals. And that's one thing that we're working on with Jen Burns' current Woodell Seal project. Finally, there are a lot of future applications that this model could be used for. For instance, the timing of life history events can be shifted in order to see how that influences seasonal energetics. Additional perturbations can be included, such as habitat loss in Arctic ice seals. The interaction effects between multiple perturbations can be considered. So, for instance, fisheries often target both large numbers of fishes, but also the larger size and higher energy density fishes. And so the interactions between prey quality and prey quantity could have a larger magnitude and will likely have a larger magnitude of effect than just changing the quantity of the prey availability. The model could be applied to other species, such as Arctic seals, or, for instance, California sea lions, who are now experiencing some population stress in California with unknown causes. And with seals or sea lions that are currently in population decline, such as stellar sea lion populations and northern fur seal populations, we can begin to test hypotheses about what might be causing these sorts of population declines, whether it's something demographic, vital rate related, and how that could be translated back into energetics and into sort of more manageable terms. And finally, empirical telemetry data can be used to back calculate the relative abundance of prey in a given year, which is of relative importance considering that we're trying to figure out how things are changing in the environment. So we can begin to use these animals as sort of indicators. My intention with this is to publish it with the code and the tables as supplementary material, and I really hope this will be useful both for people within and outside the marine mammal field. So I'm very happy after this to take questions and any suggestions you guys have for implementing my model. And with that, I want to thank my funders, the NSF grant, and my Embry Fellowship that funded my stipend throughout this 2 years. The LGL Graduate Student Research Award, which allowed me to go to Germany to take an agent-based modeling course, and an Antara grant that allowed me to travel to a couple different places to present this work. Thanks to my collaborators, Dan Costa, Kim Getz, and Michelle Shiro for providing the overwinter data that I showed you today. And thank you for the logistical support to the NSF, USAP, and several of the support contracts down in Antarctica. I also want to give a huge thanks to my committee members, Doug, Jen, and Ward. I had so much fun with these guys. You are the smartest, most fun people I've ever met in my life. I got to go to the field with both of these guys. Here's Ward with an anklet on his head. And there's Jen looking for whales with binoculars and crossing her fingers as one of my TDRs downloaded because it had a little crack in it. And there's Doug being Doug. Thank you especially especially to all my friends in Alaska. You guys have made this transition really easy for me, from pizza and half marathons to pup shearing on the Pribilof Islands to bird watching to camping. It's been a really, really fun couple of years. And especially big thanks to my family and friends in Santa Cruz and in California, and for which are here today. To my friends who've stuck with me through all my travel schedule and craziness. To my best friend Beth, and my parents and my fiance Patrick. Having you guys here today is the best. You guys are awesome, so thank you. With that, I'll take any questions.
You didn't mention how, and yet you had a statistic on mortality. So
Yeah.
how did you determine mortality in each run for both the pup and
Sure.
mum?
That's a great question. That's one of the largest uncertainties that I had in my model, was determining when mortality would occur based on given body condition. I pulled out from the literature from a couple other models who've done the same thing, similar agent-based models, where they used a proportion of body lipid relative to the starting proportion of body lipid and protein. So if the protein stores drop below a certain threshold and the animal is in starvation, drops below that threshold, then the animal does not survive. And I can pull those numbers for you if you'd like.
So it's probably easy enough if you, like that one animal you showed, early weaning,
Yep.
dead. But
Yep.
So you brought up that magical word,
Uh-oh.
protein.
Protein. Yeah. I was expecting
So what
this
happened
question.
with protein?
No, that's a great question. So especially in things like the molting period, right, where protein is obviously very important. With these types of models, sometimes it's not sufficient to just quantify energetics. It's important to also quantify the protein consumption and to look at how protein is distributed both within that animal system and outside of it. So it's something I have considered, and it's something that is recalculated with the body stores at every time step. I have the energy density of the prey items that are inputs and the amount of prey that they're getting. So they're taking in some form of protein, and then the protein is sort of being balanced and allocated to the different stores. But that's something that I'd be very interested in developing further in future iterations of the model. Yeah.
What would you predict if you ran your model through a 2-year cycle and incorporated the term for the skip reader?
That is a great question, and that's probably going to be a chapter in my PhD. One of the central questions to Jen's current NSF projects is how is molt timing and reproductive timing related, which we've sort of solved a lot of those questions. But then the question becomes, where in that year-round cycle are the important links? Is it the influence of the molt timing on the reproductive success? Is it the reproductive timing on the molting timing? And so, yeah, what I'll probably end up doing is changing my model from 365 days to 2 years so that I can simulate animals both in skip breeding and in reproductive conditions, and then looking at how that might influence the timing of their molt and reproduction based on some transfer equations that we've come up with in the field. Yeah, that's a great question. I'll report back in a year and a half. Yeah.
Can you give a little more detail on how the decision was made if the female reproduced successfully and then if lactation was successful?
Sure, yeah. So every animal in my model began as a reproductive female, so I just assumed that they were all reproductive. They all produced a pup if they were at sufficient body source to produce a pup. And then at every time step within lactation, both the pup massing condition and the adult female massing condition were evaluated to see if they were above the threshold I determined that was the threshold for survival versus mortality. And so if that pup mass at some time during lactation hit that threshold and went below that survival threshold, that animal did not survive. The mother no longer allocated milk energy to that pup, and the female was able to do whatever she wanted to do. Is that what you're asking?
Part of it. So you said they all started as reproductive females. Was it assumed that they would all carry a pup to term?
You're talking about gestation, the gestation.
Well, I was thinking about gestation and lactation.
Yeah.
So was there just a body condition? Yeah, was there just a body condition cutoff for that, and then
Yes. Yeah.
and then for lactation, did you have scenarios where the females could be in sufficiently poor condition that they stopped lactating?
Yes.
Okay.
is exactly what happened. In the figure that I showed where that one seal has a different activity budget during the lactation period than the rest of the animals do, what happened was she was at such poor condition, she barely pupped and then lactated for a couple of time steps, nursed her pup for a couple of time steps, and then the pup didn't survive, but the mom still had sufficient reserves and stores that she could continue foraging and replenish that body condition even after she sort of abandoned that pup.
Thermoregulation seems like such an important aspect of the model. From what I could tell, I might have missed this, but it seemed like you were mainly taking into account the regulation on land with conduction on the ice and convection in the air.
Yeah.
Given their high percentage of time in the water, do you need to take that into account, and would that be convection, or?
That's a great question. Yeah, and I did take that into account. I
Okay,
didn't have quite enough time. No, I didn't have time to explain everything, unfortunately. In water, it's a little bit difficult to get at thermoregulation because there haven't been any measurements on the skin temperature in the water. So we have to make a lot of assumptions about how they're regulating their skin temperature in order to sort of not lose a ton of heat to that water environment. But I assume that they kept their temperature at about 1 degree above the temperature of the water, which we think they're able to do. And then, yeah, incorporated convection for the entire surface area of the animal with the temperature of the water.
So is it a brown fat mechanism?
Of thermoregulation. Linnea Pearson will talk about that, but no, in her defense. No, I don't believe so.
And just last question, so in general we think of temperature change, climate change is harmful with change in food source and such, but with that thermal regulation, is there a point where it becomes easier for them to thermally regulate in a skid farm? Or?
That's a great question. There's been a lot of interesting work done recently with marine mammals and looking at which animals might respond differently to climate change, and some people have found that some species will actually respond positively to this predicted climate change. And so I didn't look at that specifically with my model, but it would be very easy to just run through a climate change scenario based on predicted conditions and then to measure the differences in cost of thermoregulation across two different scenarios. Yeah.
Very last question. One of your first slides showed the fishery depleting the fish by 50% in 2050, something like that.
Yeah.
How did the seals handle that in 2050?
How would they handle that? That's a great question. We don't know too much about their diet, so people have hypothesized that these toothfish are an important part of their diet. That's, again, something that Jen and I are working on right now. But because we don't know the relative importance of the toothfish to them, if they're eating 50% of their diet is toothfish, then sure, 50% depletion would probably have a very large effect. And we could simulate that by just decreasing the prey abundance by 50% and looking at the response of individuals. But because we don't know the relative importance of that diet item, it's hard to quantify that.
Thank you.
Yeah. Anyway, Lauren.
You mentioned a potential manipulation scenario for your model as being shifts in phenology.
Yeah.
How do the seals time their circannual events? What is that? What sets the pace of their circannual program? And then, given the answer to that, how much phenotypic plasticity do you think they have with respect to phenology?
That's a great question, and one that we're, again, trying to address. This is like my cop-out answer, but we're trying to address with Jen's project. Amy is looking into the hormones that could potentially regulate that timing, and we're looking at how that timing could be linked across the different reproductive categories. So I don't think a whole lot is known about the very specific mechanisms. The photoperiod is very different in Antarctica across the year. And of course, the molt timing and the lactation timing are relatively similar and close together. So I think we'll start to understand that a bit more once Amy gets all the hormone results back and we figure out which hormones are regulating the timing and how that's working. And then I'll be able to represent it a bit more mathematically in my model. Yeah, does that answer your question? Yeah.
So how about the, after the lactation period, there's that recovery period where they start feeding again before going into molting, right?
Yeah.
How important is that? That's like, so that's equivalent to the fall.
Yeah.
Essentially, like after spring, it's fall in Antarctica. And I'm just wondering, that's the time that seals in the northern hemisphere end up getting disease.
Yeah.
Not like avian flu.
Sure.
So if something were to affect that, would that affect their ability to go into a molting period? Can they delay it? Or is there like a critical amount of food they have to be able to get at that period before they to successfully get into
summer foraging period. That's been very widely debated. There are some people who think that it's incredibly important and these animals are stuffing themselves during the summer period. Preliminary data that we have from timed up recorders show that the animals are pretty active during the time they're not lactating or molting, which is a pretty short period of time. But the mass gains really differ by reproductive category, where some of the animals that skipped breeding are actually losing mass during that time. And some of the reproductive females are gaining up to about 1 kilo per day over that period. So as far as whether they can shift their timing actively, or how the different scores that they have at those different times of the period could influence their molt timing, we're still trying to learn more about that. But that's something that I could potentially have my model address if I can come up with some hypotheses about how those mechanisms might be linked.
So, getting at some of those phenological changes and things, it's one thing to look at what the intuitive timers are in that, but in order to get ecological data, sometimes it's better to start looking for the outliers of the mean rather than looking at the mean.
Sure.
And so the statisticians talk at all our meetings that we have and talk about what's the best way of expressing the mean and how the distribution and everything is. And I keep saying, no. Everything I've learned has been from outliers.
Yep.
Those that have not conformed to what the mean is. And they're the ones that are going to allow you then to add the changes in your model to allow certain animals to go into a different life history strategy, because it's going to tell you how many in the population are doing that at a given time. And so at the moment, that turns out to be a very important component of all that work that's going on, assessing vulnerability of animals to certain circumstances in climate change. And an important adaptation to that is, in fact, the flexibility in the life history strategy of the animals. Their ability, say, to go through 2 breeding pauses rather than 1 can end up with a life history that's better off than trying to breed every year or just have a breeding pause alternate year. So I don't know, my question is then, rather than the lecture here, that's a problem with a retired professor, you don't get a chance to lecture anybody anymore. None of my friends will listen to me. So my question is, are you using any of, is there a lot of that kind of within your nice normal curves you showed us? Are there stats out there for at each side of the curve, those that aren't behaving normally that you can use them for decision making within the model?
Sure, yeah, that's a great question. And outliers turn out to be really interesting in both the simulations and in the fieldwork that we're doing. Woodall seals themselves, like I sort of talked about, are very interesting from a physiological perspective in that they do skip breeding every once in a while. So trying to understand why that might be different than other seal species is really important. They live in a very extreme environment, so seeing what they're able to do to adapt to ranges that most other seals could not handle is also very interesting. As far as the simulated seals, I did use means and distributions, but I have gone through and looked at certain weird animals, so like that animal that abandoned her pup at the beginning of lactation, and looked at what the starting mass was for her and how that compared to other animals that were able to survive. And I think those are the sort of interesting things that come out of this model, in addition to the big tables and the means and standard deviations and everything. It's just looking at these individuals and following them through the simulations and looking at those